Hi, my name is Nick. I'm a junior at UMass Amherst, where I work under Professor Laura Bradley in the Polymer Science and Engineering Department. And today I'm going to be talking about my independent research project and the focus of my honors thesis, which is the solvent-assisted reshaping of multi-component compounds. So a little bit of background. Polymer particles have long been used in industry for like latex coatings, silica spheres, etc. But these particles have always been homogeneous, made out of one polymer. Or one material. The growing field now is anisotropic particle synthesis. And so anisotropic particles are basically defined by a lack in symmetry, so either physical or chemical. And this result, and for example, we have Janus particles here, which are a specific type of anisotropic particle that have two distinct phases. And so this asymmetry enables a large number of applications. For example, solid surfactants, because these two hemispheres can stabilize two different phases, essentially stabilize emulsions and prevent them from unmixing. It can be also used in colloidal assemblies. If you have some kind of attractive chemistry that you selectively put on your particles, they can assemble together into lattices or molecular analogs. Or they can be used in hydrophobic coatings. If you have some kind of rough surface on one side and then a sticky surface on the other side that can adhere to a surface, you can use this to create hydrophobic coatings. And so the main lesson here is that all these applications are still developing. None of them are commercially used yet. But what can propel these forward is the development of new synthetic techniques for these anisotropic particles. And that means accessing new chemistries, new surface structures, surface morphologies. And this will only make these applications stronger. For example, in hydrophobic coatings, if you can make a more rough surface on your particle, you can have better hydrophobic properties. And so the current synthesis techniques for anisotropic particles can be grouped into two different categories. So the first is surface functionalization, where you basically selectively put some kind of coating on your particle, on only part of it. And this may either do sputter coating, masking, or stamping. And the other group is phase separation, which is usually done using polymers, and essentially it can be done using microfluidics or some kind of heterogeneous polymerization like nanoprecipitation. And the key difference in these two techniques is that in one, surface functionalization, obviously you can't access the particle interior. It's going to be the composition of whatever your input particle was. But in phase separation, you actually do have some control over this interior of your particle, which is a whole nother set, a whole large volume you have some control over and can tailor to your specific application. So the technique that we use, which is in the phase separation group, is called seeded emulsion polymerization. And essentially what we do is we take a seed particle, we swell it with a monomer feed, which dissolves the seed polymer. And you essentially end up with a seeded emulsion droplet, which is stabilized by a surfactant in an aqueous solution. And essentially in this droplet, you have your dissolved polymer from your seed particle. And you also have your monomer and an initiator. Then you initiate the polymerization, and you can end up with a Janus particle if phase separation is complete. And by choosing different polymers, you can end up with a wide range of different morphologies. But what can happen if the phase separation isn't complete is you can end up with non-equilibrium morphologies. So in our system here, we end up with these kinetically trapped domains on half the particle's surface. And these domains wanted to coalesce with the hemisphere, but couldn't due to the rapid solidifying of the particle during polymerization. And in our system specifically, this red polymer is polystyrene. And the monomer feed that we used during SEP is composed of terpetal acrylate and also some styrene and a cross-linker divinylbenzene. And so we end up with this Janus particle here, which I'll go into more detail later on why we do this, but we use acid catalyzed hydrolysis to convert these terbutyl groups into hydroxyl groups. So a quick overview of these steps. So we make our seed particles using dispersion polymerization. Here's an image here. And then we take these homogeneous particles and we use seeded emulsion polymerization to create Janus particles with terbutyl acrylate. Then we use acid catalyzed hydrolysis to convert these terbutyl groups into hydroxyl groups. And then finally, our new technique that we're introducing with this project is called solvent-assisted phase separation, or solvent-assisted, or SAPS. And SAPS has been around and used in other applications, but we are introducing it. We don't think it's been seen before, but it can be used to reorganize particle components. So essentially, we're taking this input particle and using SAPs, we're rearranging these domains on the particle and ending up with this unique, what we're calling a jellyfish due to its appearance, morphology. And the procedure for this is essentially we do something similar to seeded emulsion polymerization, where we have a stabilized emulsion, and where we surround these particles with a surfactant, and we swell them with toluene. So toluene dissolves some of the particle, and then allows the components to move around, and then we evaporate the toluene, which leaves behind this jellyfish particle. And within our system, we can adjust the input to our SAPs and use, if we vary this seed emulsion polymerization recipe, we can see how it impacts that output. So a little bit about the mechanism. So before I go into it, I want to clarify what our input particle is composed of. So we have this one hemisphere, that's one polymer, and that is the cross-linked polystyrene polyacrylic acid that we introduced in SEP. And on the other half of the particle, we have small domains of this same cross-linked copolymer. These are the domains that are kinetically trapped and that would prefer to have mixed and coalesced with this hemisphere, but we're not able to due to kinetic entrapment. So our other phase is the polystyrene from the seed particle, and it's linear non-cross-linked. So you may wonder, how do we go from this particle to that particle? Well, here's our mechanism that we have proposed. So essentially, when we swell with toluene, we are only dissolving the LPS, because cross-linked networks do not solubilize. So these domains, which are composed of acrylic acid partially, are free to move around in this emulsion droplet. And because of the hydrophilic properties of these acrylic acid domains, they adhere to the interface of this emulsion droplet. So, and they stay there as the toluene evaporates. So eventually the toluene becomes saturated with linear polystyrene, and it solidifies. And we end up gluing these domains together at the surface and ending up with this jellyfish particle. And so we can vary the input particle using a couple different, adjusting a couple different ratios. And we can see how it impacts the final morphology. So here's what happens if we change our monomer feed composition. So essentially add more acrylic acid or less acrylic acid in that group. And when we're at a low acrylic acid concentration, the two polymers are very similar in the system. So what we think is happening is there's a very small difference in contact angle at this swelling phase, and so we end up with spheres. But as we increase the concentration of the acrylic acid, this copolymer composition is becoming more distinct from the other, from the linear polystyrene. And so this contact angle gets larger, we end up with this lip here, and then finally, once this contact angle gets large enough, this toluene droplet breaks free from this hemisphere, and we end up with kind of a messy solution where we have all the domains in their own little clumps. And so we can also vary the feed to seed ratio, which is the amount of monomer we're adding to our seed particles in SEP. And this impacts the phase separation dynamics as well as particle size. As we can see here, when we have a very small amount of monomer, the phase separation is even more incomplete. And so we don't even get a hemisphere. We still get these patchy particles. But we can see as we add more monomer, this hemisphere begins to appear, and eventually we get back to our jellyfish particles. So finally, some quick applications of our system. So essentially, these particles have acrylic acid groups on them. So these, at a high pH, these acrylic acid groups are deprotonated. We're left with a negative charge, and these groups all repel each other, which causes the hemisphere to basically balloon to nearly 3 times its size, as seen in these optical microscopy images. And so we can take advantage of this in an emulsion. So at high pH, these large particles are able to stabilize this hexadecane water emulsion, but not at a relatively neutral pH. And this will stay emulsified even after 1 month. And what's going on the small scale is that these large swollen particles are adhering to the hexadecane water droplet interface and preventing these particles from coalescing. All right, so just some final conclusions. So essentially, anisotropic particles are a growing field, and that field will only be pushed further with the development of new synthetic methods. And we think SAPS is one of them. And SAPS is also relatively simple. It's a post-synthetic process. It's just swelling and evaporation. You don't have to do that much. And we think that this SAPS can be applied to a wide range of particle systems that already exist. So other researchers and other groups that have similar systems might be able to find a whole nother range of morphologies just by trying SAPS out on their system. So for some future directions, we want to apply SAPS to some other systems and see what other morphologies we can access. And for our system specifically, we can also try some hydrophobic coding applications, as I mentioned before. So I just want to acknowledge my group, my advisor, Professor Laura Bradley, and my other thesis committee member, Professor Peter Watramo, as well as, of course, the facilities here on campus, such as in Isles, where we have our electron microscope, and of course, the shared instrumentation of the Polymer Science Department. Thanks for listening.